So the basic thing to remember is that like we can't decide which filter will be best for our image, and I mean it depends on the image specifically and the features contained in it. So we can't decide that. So we let the model decide which one to choose, and we just give all the convolutional networks. And so, okay, so here is how it is work. So first of all, here it is max pooling, and max pooling, and after and one more concept, after max pooling we apply one cross one convolution just to adjust the size of output channels, and this one cross one convolution. So we stack all the output channels of this convolution side by side, and we concatenate them, and we let the model decide the parameters so it can choose like which kernel is the best to choose from and which one is not. Okay, so yeah, any doubts until now, you can share it in the chat box, or you can like unmute and ask. Anyway, let it be. I will go over it one more time. So like basically the insight behind that is that we can't choose the which convolution will be best for our image, and so we let the model decide which convolution to choose, and the model will decide based on the all the training data and all, and it will choose which parameters for each convolution, and we'll just concatenate the output, and it will choose the best possible convolution for that. And so yeah, that is the core concept of this. Okay, so yeah, here we will do the coding part for that. So this is just importing the required modules, and after that we have just defined this convolutional block just for the our convenience. It is just like first ReLU and convolutional, and after that first. Okay, let's see. So here is the main part of that. Just for this first branch, it is just for one. It is the output for one cross one convolution with kernel size 1, and here here is the 3 cross 3 convolution, and here padding is 1. Padding is 1. It is just to maintain the size of the image as constant, and because we are concatenating the image, we are concatenating the output size, so we need to have the spatial dimension same. So we have padding equals to 1, so that the size of the dimensions of the image, spatial dimensions, will be reserved. And here this is the output number. This is the output channels of the 3 cross 3 convolutions. And in the third branch, this is 5 cross 5 convolution with kernel size 5, of course, and padding 2 just to maintain the spatial dimensions. And after that, here is the max pooling layer. So first we apply the max pooling, but max pooling won't change the number of output channel. It will just change the height. It will just change the height and the width of the image, that is spatial dimensions only. So to change the number of output channels, we will be using another convolutional block, 1 cross 1, and this is the number of output channels of the max pooling layer, output pool. And so we'll be concatenating all of these branches equals to this, and so we have used here toss.cat to all the concatenate all the outputs of that. Okay, so after that you might have you might have think of that this will be like really heavy, as we are giving all the available convolutions to the model, so it will be like really computationally, I mean, inefficient to give all of the convolutions and all. So how do we manage this? So here comes the second insight for this. The second insight is that we basically use 1 cross 1 convolution before applying any convolution, just to decrease the number of output channels, and it will maintain the it will maintain the information same, but we'll be able to do it for less computational cost. Okay, so let's see with the help of this example. Okay, so here is a 20. Here is an image of 192 channels, and with 28 by 28 size, and we have used 5 cross 5 convolution. So the number of, let's see what the number of parameters and the number of operations we have to do. So the operations will be 5 cross 5 cross 192 cross 28 cross 28 cross 32, and it will be equals to 120 million operation. And the number of parameters will be 5 cross 5 cross 192 cross 32. Okay. And so if we use 1 cross 1 layer here, the bottleneck layer, then let's see the number of operations we'll be doing for that. So first of all, we have used 16 output, 16 filters, 1 cross 1 filters uh, to do the bottleneck layer. And this is the output of the bottleneck layer, 28 cross 16. And after that, we have done the regular convolution that we wanted to do. And let's see the number of operations for that. For the first step, they are at like 2.4 million operations. And after that, there are 10 million operations. So in total, 12.4 million operations. So you can see like it has reduced to 1/10 of the original number of operations. And let's see that for the number of parameters as well. So here the number of parameters is like 15,000 only. And as opposed to here, it was like 1 lakh and 53,000. So you can see that it is really helpful for decreasing the computational cost. And probably that's why even like it is 22 layers deeper, but still as compared to AlexNet, which is just 8 layers deeper, it has like I think 1/12 of the total parameters. And so yeah, this is the final diagram of what the inception model looks like. So here is the layer, and this is 1 cross 1 convolution. This is the bottleneck layer which we use. And after that, we have used 3 cross 3 convolutions, 5 cross 5, and here max pooling. And this is to adjust the size of the output channels of max pooling layer. And okay, so we'll move on to the inception block, coding of the inception block now. So like if you guys have any doubt, you can post it in the chat box. Okay. So let's move on to the coding of the inception block now. So first of all, this is the first branch for 1 cross 1 convolution, and after that, this is the second branch. First for reducing the number of first one is of size like 1 cross 1, and this is the number of reduced channels. And after that, you have used 3 cross 3 convolution here with padding 1, and to output the number of to output this number of channels. And after that, this the another branch. So this is for the first one is bottleneck layer, this one of kernel size 1, and after that we have used 5 cross 5 convolutions and to output this much number of channels. And so the fourth branch is first max pooling, followed by convolutional block, just to change the number of output channels. And so we are concatenating it afterwards. And so if you want to see the complete Google Net, this is the complete Google Net. So here we can see that first we are first here is the first convolutional block which we have seen of 7 cross 7 size, and after that max pooling and inception block, and another inception block and max pooling and dropout, just to and dropout you might have seen dropout. Why is dropout? It is just to like make a function. I mean make the neurons independent of the features. I mean like all others like we can maintain their coexistence. So yeah. Okay, and so this is the last layer, linear layer, and this will be equal to the number of classes which we want to. This is the fully connected layer, which will be dealing with. This is the last layer, and which will output the classes, and it will be the classifier layer, and this is the forward pass for this. And yeah, so yeah, there's another important point which you have not shown in the diagram here for GoogleNet. So for if we see GoogleNet, then there is like you can see there are 1 or 2 extra errors. So like in the middle of the network. So why are they used? The basic concept behind they are called auxiliary classifiers, and we basically use them to reduce the problem of vanishing gradient, and they are also used to like classify between the features. Okay, so yeah, we'll move on now. Okay, so yeah, there are some improved versions of GoogleNet as well. So first of all, I mean, the basic insight behind the Inception version 2 was 5 cross 5 kernel. I mean, like instead of using 5 cross 5 kernel, we are using 2 3 cross 3 kernel, which will produce the same receptive field, but it will reduce the computational cost if we calculate it. And and another thing is that we'll be able to produce non-linear functions more efficiently. And there is another version 3 which has used RMS prof optimizer and factorized 7 cross 7 calculation, which means basically reducing 7 cross 7 into 3 cross 3 convolutions, and batch norm and label smoothing. And so we'll see, and there is another one like ResNet and Inception, a mixture of hybrid model. So it uses the concepts of both ResNet and Inception. Don't worry about ResNet for now. You will be covering that later in the session as well. And so, any questions till now? So basically, I will just summarize it for you. So the basically what we want to what are the insights are that we are using one bottleneck layer just to reduce the number of output channels, and it will significantly decrease the computational cost. And another insight which you can gain from the Inception model is that we let the model decide which filter will work for it the best. And that's the important point for me. So yeah, any questions? Guys, you can unmute and ask. Okay, so this was seems known as drought. So, and yeah, there are two other networks as well, which you can read about. First one is AlexNet, which is the basic one, which won the competition for ImageNet in 2012. It was the first convolutional neural network, and you can read more about it. It's just a basic network of eight layers, and there is one LeanNet as well. It is very primitive, and it has like only 5 layers, and you can read more about it. It's not very hard. And also, I'll be sharing this Google Colab notebook with you in the group. Okay, so now I think Jay will take over, and he will be covering ResNet part.
Yeah. So okay, let's start with ResNets. So so there is a problem of vanishing and exploding gradients in the convolutional neural network. So what happens in vanishing gradients? Like during backpropagation, like we update the weights by calculating the gradient of loss function with respect to the weights. But like as the networks become deeper and deeper, the magnitude of gradient becomes smaller and smaller and tends to zero. So like what happens like due to the vanishing gradients, the new weights will be like same as the previous weights. Like there will be no change in the weights, which will result in the like which will make the learning of the model to hold. Like it will not allow model to learn. So as you can see, like the 56 layer the 56 layer neuron give more error than a 20 layer neuron, 20 layer neural network. So it is because like as you go deeper, the gradients got vanished and the model stops learning. So to solve this problem of vanishing gradients, like the researchers introduced something called as residual block. So in what residual block, what we do is we introduce skip. So we skip the layer which are responsible for vanishing gradients. So let's say like these two layers are responsible for vanishing gradients. So what will we do is we will just skip these layers and we will just copy the input and put it in the output, and we will just skip these layers which are responsible for vanishing gradients. So the advantage of this type of connection is that any of the layer which is hurting the performance of the network will get skipped by the regularization, because like it is it is responsible for vanishing gradients, but we are like inputting the eh, we are like copying the initial input and we are pasting it to the output. So the layer will get skipped. The layer responsible for that vanishing gradients will get skipped. So as you can see, like with the skip connections, the network like we can find the global minima easily with the skip connection, but without the skip connection, there are a lot of local minima and maxima. So we like the finding a global minimum will be very difficult task because of without skip connection. With skip connection, we can find the global minima of the load function very easily. So here is the like the ResNet is made up of made up of blocks called ResNet blocks. So the ResNet is made up of by stacking these ResNet blocks one over the other. So a ResNet block is like made up of like 3 cross 3 convolution, which is followed by batch node, then a value layer, then again a 3 cross 3 convolution and batch node. And like if there is a change in channels from input to the output, then we have to do 1 cross 1 convolution to change the number of channels. But if the channel number of channels between input and output is same, then we can just directly connect input to the output. But if there is change in number of channels, then we have to use 1 cross 1 convolution, because like to change the number of channels. Otherwise, like we have to keep the number of channels same for both pathways. Like we have to add them, so the number of channels should be same. So here is the architecture that we will be discussing. So what we are doing here is, so we initially we have a image of dimension x comma w cross 3. Like we have height is h, width is w, and the number of channels is 3 for RGB. So what we are doing, we are first applying a 7% convolution with a stride of 3. So with a padding of 3. So and in number of input channel will be 3 and output channel will be 64. So we will get a number of channels 64 and height and number of and the height of the channel will be h and it will be w. So now what we are doing is we are applying a 2D convolution with input channel 64 and output channel 64 with a kernel size of 3 and padding of 1. And again same thing, and just see there is no change in output and input channel. So we are just directly connecting the output to the input. So similarly for the next year also we are doing the same thing. So 2D convolution with 64 input channels, 64 output channels, 3 is the kernel size and 1 is the padding. Same thing. 2D convolution, 64 input, 64 output, and 3 kernel and 1 padding. And since there is no change in the number of channels, so we are just directly connecting input to the output. So now again, like we are here, what we are doing is number of input channel is 64 and number of output channel is 128 with a kernel size of 3, and we are using a stride of 2 here. So why we are using stride of 2? Because see, we are increasing number of channels, so we are decreasing the height and width by 2. So to keep the computations slow, to keep the number of operations slow. So now we are increasing the number of channels from 64 to 128 with a kernel size of 3 and a stride of 2. And again, a 3D convolution with 128 input and 128 output channels with a kernel size of 3 and a stride of 1. So now since we are increasing the number of channels from 64 to 128, so we have to use a 1 cross 1 convolution to increase the number of channels from 64 to 128. And we are using a stride of 2 here also to decrease the height and width by 4. So again now we are doing is 128 input and 128 output with a kernel size of 3 and a stride of 1. Again, like 2 layers, same kind of 2 layers, and since not changing channel, so connecting input to output directly. So now we have a size, we have a feature size of the height is h by w, s by 2, and width is s by w by 2, and the number of channels is 128. So again, like we are increasing the number of channels from 128 to 256 with a kernel size of 3 and a stride of 2. So what like it will do, like it will increase the number of channels from 128 to 56, and it will decrease the height and width by half. So again, a 2D convolution with 56 input channel to 56 output channel with a kernel size of 3 and stride of 1. So like since there is a change in number of channels, so we are using a 1% convolution to increase the number of channels from 128 to 256 and decrease the height and width by half. So now same like 256 input, 256 output, again two layers of same kind. So now we have a feature map of height h by 4, width w by 4, and number of channel 256. So again, like we are increasing number of channel from 256 to 512. And since we are increasing the number of channels, we have to use a 1% convolution with a stride of 2 to decrease the height and width and increase the number of channels. So again, like again a decimal block with 500 input channel and 500 with 2 layers with 500 to 512 input channel and 512 output channels with a kernel size of 3 and stride of 1. So finally, we'll have a feature map of height h by 8 with w by 8 and number of channel is 512. Okay, so ahead I will discuss in the Colab notebook. Yeah, so okay, we are importing libraries needed for the architecture. So we are importing Torch, the NN module, the Torch Visions model, and we are importing transform, and it is only. And like we are using devices for like if CPU is available, if GPU is available, it will use GPU to do the computation, and otherwise it will use the CPU. Okay, so what we are defining is we are defining is REST block. So this is the one block, one REST block. So what you are doing? So if there is a downsample, what does it mean? Like if there is a change in number of input and output channels, so what will you do? If there is a change in input and output channels, so convolution one is the so like this. So see see layer two block this one. So if there is a change in number of channels, if there is a change in number of input and output channels, so what will you do is so convolution one is the this one. This one is the convolution one. This like the first layer of the residual model is convolution one. Con one. The con one is that. So what are doing if there is a change in input and output channel? So what we do is we are defining a convolution one layer with number of channels is in planes, number of output channels is out planes, and the size of 3 and square of 2 to decrease the height and width, and finally is 1. And then we are defining that skip connection. So what skip connection is, that they are keeping two layers. First is 2D convolution with kernel size of 1 cross 1, with like input channels is in planes, output channels is out planes, and a side of 2 to decrease the height and width, and a batch node like to keep to avoid like overfitting and like if we are not decreasing the number of input and output channels, so what will we do is we are just like convolution one will be number of in planes, number of out planes, kernel size of 3, and this side of 1 and pending of 1. And identity will be like there is only skip connection. There will be not, there will be like no convolution and no batch node because we are not changing the number of input and output channels. And like convolution two is this thing. This thing is convolution two. But this is convolution one. This is convolution two. This is batch node one. This is batch node two. This is value. The value function like. Okay, so we are defining so identity. So we have input here. We have input as x. So identity of x is this part. So identity of x will what will you do it? If there is no change in channels, it will just paste the input to the output. But if there is change in channels, it will do 1% convolution and batch node, then it will just copy and paste the input to the output. So identity is input like this path. Now what we are doing is we are input like we are computing convolution one, then batch node one, then this value again convolution two, then batch node two. And now what we are doing is we are adding both the channels from both paths, like from this normal path and from this skip path. So we are adding both the outputs from both paths, and then we are doing the value of that. So now we are stacking these graphical blocks one over the other. So now we have a input of h. We have like input of h cross w cross 3. So now first layer will be we are increasing the number of channels from 3 to 64 with a kernel size of 7, stride of 2, and padding of 3. Then we are using a max pooling layer to decrease the height and weight, and then batch node and then a value. So now here the residual block will start. So now in layer 2, what we are doing is we are doing a residual block and like in we are with input channel 64 and output channel 64. So there will be no change in number of channels. So that's why downsample is false. Similarly, again a residual block with 64 input, 64 output with a downsample of false because there is no change in number of channels. Again a layer 3 with input channel 64, output channel 128. Now since there is changing number of channels, downsample is true. So downsample true means we will use this thing. We will use identity as one convolution with a batch node, and convolution will be 3 cross 3 convolution with a stride of 2, and in channels and out channels. So like we are doing this with 5 layers. So in third layer, what we are doing is we are increasing 64 to 128. Then downsample will be true because changing number of channels. So and again a block with same input and output channels. So downsample is false. Again a layer 4 with number of input channel 128, output from 2 to 56. And since there is a change in channel, downsample is true. Again like 256 to 56, downsample is false. And layer 5 also we are increasing 256 to 512. Now what we are doing here is we are doing global averaging. So like if like whatever will be the height and width of the number of the channel, it will make it will make all channel as a single number. So like it will average the global average. It will do global average, and for a single channel it will output a one number. So like in the like this thing, in the end we have this h by 8, w by 8, 512. So after that pooling thing, average pooling we will have 1 cross 1 comma 1 comma 512 of feature map. We are just forwarding the input. Like first we are putting it into layer 1, then layer 2, then layer 3, and then layer 5. Then we are doing average pooling. Then we are just fully connected. Like we are keeping it a fully connected. So we'll have fully connected is. So after average pooling, we have 512 channels. So what we are doing fully connected is we are changing 512 channels to number of output, the number of classes we want, to classify. That will be the output number of classes. Okay. Okay, so now we are really training our network. So what we are doing, number of epochs is 100. Learning it, I set it to 0.001. Then we are applying random transform. We are padding it. We are doing padding. So padding is it will apply a four padding of four on each side of the image. So random horizontally, we are flipping the images randomly horizontally. Random crop is we are cropping the images randomly. So to make the model more robust, so it can act good on other data sets also. So we are now transforming the image to tensor, to PyTorch tensor. So we will be training our model on CFIR 10 dataset. So we are importing that dataset, training dataset and test dataset. So now we are creating a data loader which will divide the dataset into batches. We are creating a batch size of 100 for both test and train. So we are using cross entropy loss and optimizer. We are using ADAM. Okay, so now what we are doing is we are training our model and we are just printing a loss after every after every epoch. We are printing the loss what we have what is the loss after every epoch. So now we are testing our model. So model.eval will evaluate our model with source.nograd means we are stopping the model to we are okay, say we are stopping the gradient. We don't want our model to do gradient descent now. Now we want our parameters to be fixed. So with no grad, we are just testing our model with accuracy. So I got a accuracy of 85.16 on the ResNet 18. This is the ResNet 18. There are many other variants also, such as ResNet 34, ResNet 120, ResNet 56. So, as you increase the number of layers in ResNet, the error will decrease. But in other architectures, what happens is as you increase the number of layers, the error increases. So that's the benefit of ResNet. So the main benefit of ResNet is it introduces the skip layers. So if any of the layer is responsible for vanishing gradient, it will just skip that layer and it will provide alternate way for the gradient to flow from input to the output. So that's the thing. If anyone has doubt, they can ask. So if there is no doubt, there are no doubts. If there are no doubts, then I will call Ansul. He'll discuss strategies for training neural network.
Hello everyone. But I'll just present my slides. First, I'll share my screen. Okay, I guess my screen is visible now. Is my screen visible?
Yes, I'm sure.
Okay. So okay, I'll be teaching strategies for training neural network. So when we are improving our AI models, so there is no one size fit all model strategy. Basically, there's no one strategy that you can use to get the right answer. You can't be like, if I use this model, I should every time get the right answer. And also there exist certain parameters which have to be accounted before you move further, because you can't use the same parameter criteria for each of your models. So you have to choose the right training parameters and metrics in order to get the right results. So we have already learned what backpropagation does. Here we initialize some random weights, then we forward propagate those values, and those values pass to the hidden layers and generate an output. Now we compare the generated output with the actual output, and then we generate a loss function. Now when the loss function generated, the backpropagation algorithm tries to adjust the values to match the expected output. But there are some problems here involved, which we'll discuss in detail. So for example, I've taken an example of a neural network where we are trying to predict whether a person will buy insurance or not. So here we have 4 input criteria that you have taken: age, education, income, savings. And the hidden layer here is awareness and affordability. These hidden layers are extracting features, basically like age and education, they can impact the awareness. Income and savings here can affect the affordability, right? So if we train this neural network by giving some initializing some inputs, let's say we're giving 29 beat as age, BTech as education, 150K as income, and 25K as savings. So what we do, we pass these values and the forward propagation occurs, and then we get some result. So now comparing with the actual result, we start backpropagating. So what we are doing in backpropagation, we are updating the weights. So let's say if we want to update this W9. So this W9 is a weight, this is the 9. So W9, we'll be subtracting a small portion of it. That will be the learning rate multiplied by the gradient. Okay. So the gradient here will be the del loss over del W9. Now this is the learning rate which we are by which we are subtracting, so that we are trying to minimize the loss function here, because our end goal is to get a better model where we can reduce the loss as maximum as possible. So now W9 trains as this. Now if you go to the next inner, if you go more inner, so we get the same W1 minus learning rate into gradient. So here the gradient will be multiplication. It will be a multiplication of the del loss over del awareness and the del awareness and del 1. Okay. So this way, if the number of layers keep on increasing in the neural network, then multiplication will also increase. So as the backpropagation keeps going backward and backward, the gradient, if it is smaller, it'll keep going smaller and smaller, and it'll eventually reach zero. After it reaches zero, the input layers that are the hidden layers that are inner to that layer will not update for any value of the gradient, right? So this is what is called a vanish gradient problem. And on the contrary, if we have the gradient, here we had a smaller gradient. If the gradient keeps on increasing large, the parameters will start fluctuating so much that the changes updating values will be too random and too large. So that would be the exploding gradients problem. So now vanishing gradients, why do they occur? See, we have certain activation functions. See, we are considering a sigmoid function. In this function, we can see that function values from 0 to 1 itself. And its derivative, we can clearly see it's very close to 0. So basically, it literally has very small gradient. And if we keep propagating it, and learning rate itself is very small. So if we backpropagate and subtract the gradient multiplied by the learning rate, then the value will keep on going smaller. The function this is how the vanishing gradient problem arises. Similarly, the opposite case might be for the exploding gradients. Now, how do we know whether our model is suffering from this problem? See, for exploding gradient, the model weight starts growing exponentially. For vanishing gradients, it shrinks exponentially. And for exploding gradients, the model weight become no longer a number during the training. But in vanishing gradient, it might reach 0. And here we have an avalanche learning, basically because there'll be so much fluctuating, because the learning parameter, it'll keep oscillating the graph before it can ever reach the center. So that will be it'll be very drastic learning. And here it may slow down and it may eventually stagnate as well. Now, how do we solve? Now we know that our problem is arising because there are so many layers. So naturally, what we can think of the first thing solution is we should reduce the number of layers. because if we reduce the number of layers, the multiplication of gradients will reduce, and hence it will solve the problem. But reducing layers won't solve the problem, because if we are reducing the layers, we are giving up on the model complexity. Because the more the number of layers are, the more capable the whatever neural network that we are designing, the more capable it becomes to represent whatever the mappings that we're trying to create. So reducing the layers won't effectively be solving the problem. So we rather use, see, we use saturated functions like sigmoid, right? Instead of that, we can think of using non-saturated activation functions like ReLU or leaky ReLU, because these won't saturate to, let's say, 0 or 1 as in case of sigmoid. So these won't decrease exponentially like sigmoid decreased. Then another method is gradient clipping. This effectively solves the problem of exploding gradients. So during backpropagation, if we have a gradient value which exceeds certain limit, then what it does is it clips the gradient to the limiting value. Let's say this is the syntax. So here we have written clip value to be 1. So what it does is, if any gradient value is exceeding the value of 1, let's say -1 to 1, if it's decreasing -1 or exceeding +1, then it will clip it to 1. Let's say, for example, if we have a zero, we have a, let's say this is a gradient vector 0.9, 100. So 0.9 is along the x-axis, 100 is along y-axis. It points mostly towards y-axis. Now, if you just apply the clip by value gradient function, then it'll clip it to 0.9, 1. But there's a problem here. It will no longer be the same vector. The direction has completely changed. So we modify the solution by using clip norm instead of clip value. Clip norm will reduce both in the same proportion. So basically 0.9, 100 will turn to 0.0089 and 0.995. So basically it clipped the gradient effectively, and thus we are preserving the orientation as well. Now we'll deal about a problem which often arises in ML. So the problem would be if your device underfit or overfits your data. So let's consider a simple classification example. Here we are trying to classify our image, whether it's a circle. Let's say the circle is one class and triangle is the other class. So we are trying to separate the features so that we can classify whether a particular given test data belongs to circle class or the triangle class. So first we can train a very simple ML model, which is basically a simple threshold. So if value is greater than this threshold value, it will classify it as triangle class. If the value is less than this threshold, then we'll classify it as a circle class. This might seem the best solution, like it's very simple and it's very fast and it might work in most cases, but it is actually not very accurate. We can see in the graph that it will not work and it may not work on the unknown set, which is a test set. It fails to capture the trends that we have in the data. Basically, it just makes a line and checks the value of the x-axis. So we are not really looking into what the model is dealing with. So we'll not choose this. This is what underfitting is. Underfitting does precisely this. It doesn't capture the trends in the data. Now, if we use a complex ML program and try to train it, after a while, we'll see that it does a good job. It is separating properly the circular class and the triangular class. This is the proper fit. But if it, however, with the neural network, if we let them train for too long, they begin to overfit the data. That is, it tries to capture each single occurrence. See, the graph turned to get in that circle. So it tries to capture every nuance. Maybe it may be the wrong, we should not be reading that value, but it still captures all those wrong weightings as well, leading to overfitting of the class. So this will give good results with the training data, but it cannot generalize it to untrained data. So now, how do we know if our whatever we have coded has this underfitting or overfitting problem? So we can look at it, but how well the model will perform on the training data and the validation data. So we could use the test data instead of the validation data, but if we use the test data for each parameter that we change, it will tweak the model and it will cause some unknown errors. So we are using the validation data. So spotting in underfitting is clearly easy because we can see that the model simply won't give the right results. Accuracy is close to, like, say, 20%. So that's actually not a good case. In an ideal case, if you want to consider, the model generalizes well and trains well. So you can getting 100% is unlikely, but 80 to 90% of both training and validation set accuracy will imply that the model is properly fitted. However, overfitting will happen if it picks some weird nuances which come in the problem state data set. So what we can see is the validation data set accuracy is much lower when compared to the training data set. So this will help us identify this problem. Now, how do we solve the problem? Solutions for solving the underfitting. So here we can we can train more data. Basically, what it means is we didn't receive enough data, and we can try to have more data in order to for it the model to develop a complex understanding of the situation. Then we can also try using different features. Let's say if we fix one or two features as the parameters for classifying whether it's underfitting or whether the model is giving the results for that, this might lead to underfitting. So we'll try to use more features so that we can have a better model predicting the values. Now, train for longer times. Sometimes what happens is model just needs a longer time to train. There are many cases, let's say for object detection. Object detection cases usually have some 20,000 epochs and they take nearly half a day to run. So maybe not considering that long, but we can train for a longer time than the model is running for. That can effectively make the solution better. Or we can always go for a better model because just maybe that our model is not the right approach for solving the problem. Overfitting. This is more of a difficult situation to solve and can be very tricky. So one trick is we can get the more data, which is effectively what normal thing will do. But getting more data we should make sure that the data we get is evenly spaced out. We should not be getting only the solutions category for, let's say we consider the binary classification. We should not have the data which has more of the triangular class than of the circular class. We should try to get an evenly spaced out data. Now, another thing is early stopping. We might think that since the validation data set starts going down after some time, what if we stop it early? Well, this temporarily solves the question. It's more like a band-aid. It can eventually wear off. So if you stop it early for now, fine. But eventually, while you're training the model later on, it might eventually lead back to the same overfitting problem. So early stopping won't solve the problem. Then we can reduce the model complexity, maybe reducing the number of layers, because we know that reducing the model complexity by layers or reducing the number of nodes will help solving the problem. Add regularization terms. Regularization, which we have already discussed in our earlier session, is a technique where we are using the loss function. By penalizing on the loss function, we are using more complex models to overcome the overfitting situations. Or we could use something called a cross validation. Basically, it's a method where in our data set that we divide our data set into two components, which is the training data and the test data set. So we train a model on different iterations. Basically, we use training data for some iterations and we basically divide the data so that we can train selectively. Then we have the ensembling. Ensembling is a great technique, just it requires a lot of time. So here we combine several models. Let's say we have a data, we pass it through model A, B, C. Okay. We combine all the three readings to produce one optimal predictive model. The combination we can be like usual average, or we can be like maximum, or any such function we can use our own. The next is dropout layers. Dropout is a technique where in the neural network, we randomly ignore some outputs. It may seem that since we are losing out random iterations, we might be losing the data, but we are not, because the others make sure that we retain the lost data. So these are the ways in which you can reduce the overfitting problem. Because see, I'll explain that again. So if you are losing out some of the neural network, some of the nodes, then you're effectively increasing the percentage of load on the other three to be bearing the weight of the entire problem there. So we are effectively reducing the number of iterations and enhancing the weight on each iteration. Okay, so these are some ways in which you can try solving it. Basically, it's all about a little bit of guesswork. You should try what you're trying to implement. If it doesn't work, try to look for alternatives and try to come up with solutions. So now let's move on to the next parameter that plays a crucial role: hyperparameters. They effectively the user is the one who defines them, and they control the learning process. So for example, this is learning rate. Learning rate is a parameter which will control how the model will change to a certain situation, like by how much will the weights be updated. If we set the model weight to be like 0.1, so it will progress in 0.1 delays. It will progress at 0.1 intervals. If you put, basically it tells us by how much every time the model should be learning, the percentage learning every model. Now And it should neither be too small or too big. If the learning rate is too small, then the model will take a lot of time to learn. And if if the learning rate is too big, then it will learn too fast. Maybe it will lead to again situation what is known as the overfitting. Sorry, exploding gradient, because that's what the problem. If you learn too big, then the parameters will multiply and will lead to overfitting. Sorry, exploding gradient problem. And we can also use adaptive learning rates. These are usually used in the adaptive optimizers, which I'll discuss about later. So this is how we can use it. Now, moving on to the optimizer. Optimizers can be of two types mainly. Gradient descent. Another one is adaptive. Adaptive ones, so the difference in these two is that based on how they tune the learning rate. If the tuning is done manually, like if we are particularly giving in the learning rate, then it is a gradient descent algorithm. But if the tuning is automatic, then it's adaptive algorithm. Now, how do we decide which optimizer to choose? So the gradient descent algorithm has SDD, AdaGrad, RMSProp, which you have already learned. Adaptive has ADAM, AdaDelta, AdaBound. Now, if we now let's say SDD. SDD is very basic, but and it's rarely used. The problem is that on encountering saddle point, it is not able to escape them because saddle point has a they are not the local minima, but it is not able to escape them due to the drop in the function there. But if you use it alongside the momentum, it will give work better and give better results. And in several problems, we usually have the critical information which is sparse. It's not fully crowded. We have sparse data. So in those cases, using ADAM can be useful. Sparse basically means that the data set will have a lot of not a number values. Basically, no values will be there for some data. Now, next will come to the batch size. Batch size means the number of samples that you're processing in one epoch before you're updating the weights. So let's say if you take 1050 samples and you want to set up a batch size equal to 100. So what algorithm will do is it will take first 100 samples from the training data set and trains them, then trains the network. Then it will take the next 100 samples and train the network. We can keep doing this till we propagate all samples. A little problem arises because there are 1,000 but only 50 remain. At terminal epochs, we reach 1,000. Then we can consider the last 50 samples to be the last one more epoch. Then we will train the neural network. So what are the advantages of using a batch size less than the number of samples? One thing is it will require less memory because we have this memory allocated. If you use the entire thing as once, basically if you use 1,050 samples all at once, it would require a lot of memory. And that could not be sometimes the memory limit might not be that great to support that much memory. So this effectively reduces the memory and trains network faster because network based trains faster with mini batches because we are updating them more frequently. Here in our example that we have taken, we have divided into 11 epochs. So basically we are training the network 11 times. So it is able to update better and give better results. Now, what are the disadvantages of using batch size less than samples? The thing is accuracy as well decreases because the smaller the batch size, the lesser will be the accuracy. Now, this is one graph where we have the batch. Batch here refers to the full batch where you are taking the entire 1050 as one epoch. Mini batch is basically the one that I told, 100 batches. 100 is the batch size and we are having 11 iterations. And stochastic is a specific case of mini batch where batch size will be one. So you can see that it is training a lot. The stochastic, the red line, is training so many times, but that it is giving such wide results that we cannot determine the conclusion. Mini batch, on the other hand, is deviating much, but we can at least predict where it's going. And batch, since we are training the entire thing at once, so it won't give much variations at all. So anyone has any doubts till now? Okay, if not, I'm proceeding to evaluation metrics. So the idea of building machine learning models works on a constructive feedback mechanism. So basically you build a model, get feedback from the metrics, make improvements, and then continue till you get an accuracy that you desire. Okay, so evaluation metrics basically explain how your model is performing. The choice of this metric depends on type of model and implementation plan of your model. So let's look at some of them. A confusion matrix. A confusion matrix basically an n cross n matrix where n is the number of classes that you're predicting. There are certain definitions to be remembered. For now, let's consider n is equal to 2. So this is a confusion matrix. It represents 4 possible outcomes of a classifier. They are true positive, true negative, true positive, false negative, false positive, and true negative. So there are two basic, I'll explain what this is. There are two sets of values. This is the predicted values, is what our model will predict. And the actual values are those that the target value of the data collected. So let's consider this image. Here, if the model, this is, we are basically considering an example where we are trying to predict whether it's the cat or not. So here, if the model predicts that the image as not, if the model predicts that the image is a cat and it actually is a cat, then it is called true positive. Now, if the image predicts the image as not a cat, but the actual value is a cat, then it is called false negative. Now, if the if the model predicts that it is a cat, but actually it is not a cat, then it is the false positive. And if the predicted value is, it says it is not a cat and it actually is not a cat, then it is a true negative. So basically, true positive and true negative are the ones which will enhance accuracy of our model, and false negative and false positive, they reduce the accuracy of our model. Am I clear with what this confusion matrix is? Because we'll be using this confusion matrix ahead. So please let me know if you have any doubts. Unmute yourself and ask if you have doubts. Okay, I shall proceed if considering no doubts. So before we know what this does, okay, so this is the confusion matrix. Here we'll discuss some terms that are important for this. So we have accuracy. Accuracy, it stands for proportion of the total number of predictions that were correct. Basically, it is sum of the true positive and true negative, true positive plus true negative divided by the total predictions that the model is making. That is what the accuracy is. Then precision. Precision stands for proportion of positive cases that are correctly identified. Then the negative value the negative prediction value. So precision was this positive prediction value. It says the total number of correct positives that were identified as correct. Now negative prediction value is a proportion of negative cases that are correctly identified. So basically it's D by C plus D, which is a true negative divided by true negative plus false positive. So this is what negative prediction value is. Then the recall. Recall stands for proportion of actual positive cases that were correctly identified. So basically recall stands for the sensitivity of the total positively predicted cases, how many were correct. So that's what A by A plus C tells. And then there is specificity. It stands for the proportion of the actual negative cases that we correctly identified. So B and D are the cases that we identified as negative. Of those, only D are the cases which are correctly identified. So it is D by B plus D. So this is what specification is. So in general, we'll not be using all at once everywhere. So we'll be concerned with one of these maybe. So let's say if you want a pharmaceutical company, so they would be concerned with having a higher specificity because they should make sure that they don't get false negative values, because the false negative will cause problems in the medicine wise. So now this is recall and specificity I already discussed. Now then we have an F1 score. It is basically an harmonic mean of the precision and the recall. So here what we're trying to get is the best precision and recall at the same time. That's why we're using the harmonic mean. So you might question why we are not using the arithmetic mean. Arithmetic mean, if you use on the confusion, it might lead to problems because when the precision is 0 and recall is 1, so arithmetic mean will give us a 0.5 F1 score. But can we have precision 0 with having recall 1? That's an invalid case. That's why arithmetic mean fails. So we use F1 score, which is a harmonic mean. Next, we have something called the Kolmogorov-Smirnov test. This measures the performance of a classification model. More accurately, it tells us the degree of separation between the positive and negative distributions. If the scores are able to partition, basically if you are able to divide the population into two separate groups, where one has all positive values and the other has all negative values, then the KS, that's the Kolmogorov-Smirnov value, will be 100. On the other hand, if we are not able to differentiate between the positive and negative, like if we randomly classify them, then the KS value will be 0. So, and as we can understand, higher the value of KS, the better the model is in distinguishing the cases. So here we can see a plot of percentage cumulative good and bad. So here good refers to the correct classification and bad refers to the wrong classification. So the largest difference between these two graphs is what will give us the maximum accuracy of this test. So next we have AUC ROC. AUC ROC curve is basically a probability curve. AUC stands for area under the curve. So it's basically a probability curve of TPR against FPR. TPR here stands for true positive rate. FPR stands for false positive rate. So we are trying to make a probability curve of TPR against FPR at different thresholds to separate the signal and noise from the given input. So it is basically measures the ability of classifier to differentiate between target classes. Here the target classes are basically in that binary classification problem that I chose for the example of identifying a cat. So the cat and not a cat are the target classes here, which we are trying to measure using AOC. So it basically we can understand that greater the value of AOC, the better it is its ability to distinguish. So now this is a sample graph and we are trying to know what this ROC curve depicts. So here we have the true positive rate. We have plotted against a false positive rate. So in ROC curve, a high ROC value basically means a higher ROC curve, a higher X value, which is a false positive rate. A higher X value indicates that there's a decrease in specificity, while a higher Y value will indicate an increase in sensitivity. I'll repeat. If we are moving further towards the right in the X graph, it will mean we are decreasing the specificity. And if we move further high up in the Y graph, we are increasing the sensitivity. See, point A. Point A is where the sensitivity is highest and specificity is lowest, as I told earlier. Now, if I move to point B, we can see that we have moved left along the x-axis. So point B also has the same sensitivity as A, but its specificity is higher. And point C, we have moved down the y graph and also to the left along the x-axis. So point C has lower sensitivity than B because we have moved down, but it has higher specificity because we have moved left. Then we have the point D. Point D, since we have just moved down and not moved left, the specificity remains same, but sensitivity decreases. The point T has the highest specificity because here along the x-axis we are at 0. So, and I told the more we move towards the left until 0, we are increasing the specificity. And since from D to E we have not moved down or up, its sensitivity remains same. Now a question. Going by this logic, can you guys tell where the point corresponding to a perfect classifier would lie on the graph? You can unmute and say. Someone? Okay, as many of you might have guessed, it will be the top left corner of the ROC curve, because we know that along the x-axis, if you move right along the x-axis, we are reducing the specificity. So if we need to have a perfect classifier, we need the specificity to be max and sensitivity also to be max. So that's possible only at the top left curve. So this is what now I'll be using a Colab where I'll be telling about the evaluation metrics. Everyone following me till now? Anyone has any doubts? Okay, I'm assuming no doubts. So I'll proceed with the evaluation metrics. So evaluating model is a core part of building an effective machine learning model. So here we'll be using a model and checking the evaluation metrics. So first we'll start with importing libraries. So import NumPy and Pandas. You must have already used what these two are. Then sklearn. Sklearn is simple, effective tool. We use this for predicting the data analysis. Basically, to get the analysis of the data that we're using, we use sklearn. Seaborn, as you already know, it comes along with Matplotlib. ITER tools, it used to iterate over our data structure because we repeatedly run over the entire data set. We use ITER tools while we are trying to use the ROC curve, while we are trying to plot the ROC curve. So we set the figure size to be 8 cross 8 and SNS stored type ticks. Ticks basically means that on the x-axis and y-axis, you will have the marking of 0, 1, 2. If you label the x-axis and y-axis from 0, 1, 2, 3, it'll have the marking of that 1, 2, 3 rather than having a clear graph. So for this, we are taking a data set. We'll use breast cancer data set. This data set is used for binary classification between two types of cancer, which is the malignant and the benign cancer. So first we'll do is load the breast cancer data. We have already imported this function from the sklearn data set. So it's already an inbuilt data set. So we'll load the data set. And just to give a brief, we'll see the description of the data set that we have. So this data set has a number of instances is 569, attributes is 30, and predictive attributes in class. In the attributes, we have radius, texture, perimeter, area, and all those things. So these are all the attributes. So we'll see what the target classes are. Target classes means since you're using a binary, so what are we going to target for? So basically we are going to target for the two types of cancer, right? So we are trying to just have a look at what are the two target classes. We print the target classes, we can see, wait, I'll run them. So I've loaded the data set. So if you print the description, we get the description. Now if you print the types of cancers, so these are the type of malignant and benign. So as we can see above, the dimensions of the data is 569. So it means there are 569 examples and each has 30 attributes. 30 attributes. The target basically is binary. If we have 0, then it's malignant. If it's benign, then it is 1. So now we are storing the data, the features of the data in the X and the labels of the target, basically 0 or 1 value on the Y. So if we print the shape, we can see shape of X is 569 cos 30 because there are 569 images and each has 30 features. And shape of target is 569 comma default it's 1. So basically the Y stores the 569 images on the rows and each has only one value with 0 or 1, where 0 means malignant and 1 means benign. So, and since we have a data set, we can't be using the same data set to train as well as test our model. So we'll be splitting the data set into training set and the testing data with 369 examples for training and 200 examples for testing. So we are training. So stratify, this is a function that we use, train test split. So we are splitting so that test size should be 200. Random is used for reproducibility of the code. Stratify ensures, since we are splitting the Y, we should ensure that we split it such that the same proportion of the binary classification is preserved in each class. It should not be like we should not be classifying it as all that are benign should be in one test class and all that are malignant should be in the training data. So we are ensuring equity in that. Now I print and check the first 10 values in the Y train. So I can see these 4 means it is benign. This means malignant. 3, these means benign. This is malignant. This is benign. Now training and predicting value. In this example, we'll be using Skillet's support vector machine classifier, SVM classifier. As you might have already learned, it's a classifier where it's a binary. We can use it for binary classification as well. Here we are predicting whether it's benign cancer. This class is used from sklearn.svm. So we are using this to predict the suggestion. You can also try other models on your own. Where you can search for online of the different models that can be used. So here I'm using a classifier. Here, this kernel here, kernel is it's used to take the input that we are getting from the data, and it transforms transforms that input into whatever form that we require. So it basically transforms the training data set so that a nonlinear surface is able to train. If you have a nonlinear, basically if we have a data set in which it tries to you give a proper line, a linear. Basically, if you have set the kernel to linear, we are trying to get a linear equation such that we are able to classify the two sets of images that we have got. Basically, it will help us to get a linear function so that we can divide the data, we can classify it as benign or malignant. And verbose is basically a choice to see what and all, so that we can study our output as the model trains. So next we'll fit the train the model on our data set. Since it is very small data set, so it will easily train it quickly. So it is doing the classification work. Okay, so classification done. Once you have done the classification, we should now make the prediction. Basically, now we have used the training data set to classify the model. Now we are going to test it on the test set. So for test set, we have two results. White underscore TREDS. It is a one-dimensional vector where we store whether it is malignant or benign by using 0 or 1. So basically, it's a one-dimensional vector because it stores either 0 or 1. And then we have the Y prob A. It is 2D vector where it's a vector of length 2 where we are showing the probability of it being malignant and probability of it being benign. So we can classify, so we can predict the class for data instances using a model using predict function. So this gives us a class prediction. Okay, first it's important to know there are two types of outputs, a class output and a probability output. A class output, SVM uses a class output. Here, if we have in the class output, we get a straight value. In our case of binary classification, the class output will give us 0 or 1. And probability output means it gives us a probability of each output. So basically here ypreds gives us a class output and yprob will store the probability output. So we are using the two functions predict, which will give a class output, and predict underscore prob will have the probability output. We run it. Now in the probability output, we have two values, right? So now we are trying to convert this y prob into a single vector so that we can just know whether the probability of it being a benign cancer. So we are reshaping the model to get, so double colon means we are using it for all rows, and we one is a column index, and we are reshaping whatever was there to a single column. And then we are just printing and checking what are the first 5 values of prob A, PREDS and Y test. So we can see that a probability that we are giving quite accurate results, and probability is like 99%, which means it's benign cancer, and 0.0 means it's closer to 0, which means malignant. Similarly here, these three are close to 1, so it is benign cancer. Now let's calculate the confusion matrix of product of whatever we have predicted. So this confusion matrix can be used using the sklearn matrix confusion matrix. So we can use the direct function matrix or confusion matrix where we pass the Y test, and basically we pass the test results and the predicted value, our predicted results. Test results are what was initially there in the data set, and ypreds has what we have predicted using the classifier model that we built. So this gives us the confusion matrix. It's difficult to understand here. I shall plot it soon. So instead of using this direct function, we can ourselves make the confusion matrix as well. So we make a function to get the confusion matrix where y true, and we pass the y true and the y prediction. So basically we are passing the two arrays which have, one of them is y true, basically means what our actual output is, basically the target output. And ypred is our predicted output. As I told in the slides that as I told in the slide that y true, we have one thing called a model output, actual output and the predicted output. So here y true is the actual output and ypred is the predicted output. So we make n classes to get the length. So y true has only two values, 0 or 1. So unique will be 2, there will be two values. So we make a confusion conf is a two-dimensional array. We are making a 2 cross 2 matrix, basically where we'll be storing the confusion matrix. So we are here making a 2 cross 2 confusion matrix. So now in whatever the y true and ypred, we are making such that, okay, now I'll explain on the plotting of the graph. Just leave it for now. I'll explain what that does later. So one thing, I got to run this. So if I run this and run this, okay, I got the same confusion matrix. Now I'm going to plot the confusion matrix. This is rough code, basically a simple code to how do we plot it. Now this is the confusion matrix. Now here I was talking about how y true and ypred, how does it increment the value at, you can see these values, no? How did it generate those values from an empty set in conf? So when it is y true and ypred, it will count at location int actual int pred plus equal to 1. So basically, if let's say y true is predicted as true, so basically it will be 1, and y pred is also true, then it will be 1 cross 1. So we can see 1 cross 1 here corresponds to true positive. So it will update it there. Similarly, if the true value is 0 and predicted value is 1. So basically, if we make a wrong prediction, if true value is 0 and we predict it to be true, then it should be false positive. So true value is 0 and we predict it to be 1. This is false positive. So that's how this function is here. This loop here is incrementing at the right positions. Am I clear with that? Okay. Now here we can see 1 comma 1. This is the true positive. This is a true negative. And this here is a false positive. And this here is the false negative. Basically, easy way to remember this false positive is wherever the predicted label is positive, we retain the name positive and add true or negative based on whatever the true label is. And similarly, wherever this predicted label is 0, that is negative, we retain the label negative and we add true or false based on what the true label is. So this is the confusion matrix that we have plotted. Here, for further, instead of referring it as numbers, we'll be storing it in variables. PP is true positive, TN is true negative, FP is false positive, FN is false negative. So now we are going to do the metric analysis. So to store all these metrics, let's create a dictionary results. So results will be the dictionary where we'll be storing all the values. Accuracy. Accuracy is already told. It is total number of examples correctly predicted by the total number of examples. That is, it will take true positive plus true negative divided by the total reading. So we are running that. So if we run that, we can see accuracy is close to 95.5%, 0.955. So that's the accuracy of our data. Now true positive rate. True positive rate means number of samples which are actually positive and predicted as positive divided by the total number of samples that were actually positive. So what it means is, so actually and predicted positive means this, and which are actually positive, it means this both. So we are trying to find the ratio of 123 divided by 125. Just so the total positive true positive rate is 0.984. Now true negative rate, number of samples actually and predicted negative divided by total number of samples actually negative. So what we read here, true negative means predicted and actually negative refers to this light green, and which were actually negative is this and this. So it is 68 divided by 68 plus 7. So that is the true negative value, which is also known as specificity. So we get it to be 0.907. Now positive prediction value. It is the number of samples which are actually and predicted as which are actually positive and predicted and positive divided by total samples which are predicted positive. So this is slightly different from the initial recall that we defined here, the true positive rate. Here we are taking actually and predicted positive divided by those that were predicted positive. So here it will be 123 divided by 123 plus 7. That will be the positive prediction value. So if we run it, you can see that the positive prediction value is close to 0.946. Negative prediction value. So this is number of samples actually and predicted negative by total samples predicted as just negative. So this will be the 68 divided by 68 plus 2, because the predicted as negative were 2 and 68. So negative prediction values here. So if we run this, you can see it's 0.971. Okay, so now we have done all the basic predictions. Now we are moving on to F1 score, where we are trying to find the harmonic mean of precision and recall. So precision was, this is a true positive rate is the sensitivity of the recall, and precision. Positive prediction value is the precision. So we are generating an F1 score using harmonic mean of precision and recall. So we get this as the F1 score. Now Matthew correlation coefficient. This is something new. This value ranges from -1 to 1. Here 0 would mean that we are using random prediction, not basically predicting anything. So 1 would mean it's a perfect classifier, but if it's a negative value, then it would mean this is negative correlation. What is negative correlation? Basically, it means that there is some sort of disagreement between what we are predicting and what we are observing. So basically, a model is not giving a right classification there. So this is the formula for Matthew correlation coefficient. And we can see that it is 0.904, which is very close to 1. So our model is almost a perfect classifier. Now we'll use the ROC. ROC stands for Receiver Operating Characteristic Curve. ROC curve, we are plotting the diagnostic ability to discriminate the threshold values. So the ROC basically, as already discussed, it is plotting a true positive rate against a false positive rate at various threshold. So we'll plot the ROC curve for the breast cancer. So this is what we are implementing, whatever the ROC curve that I discussed. We are trying to make an array for true positive and false positive rate and trying to find out the values of this true positive rate and false positive rate at every instance. So delta 0.1. So what is delta is doing? Delta is calculating the difference between each threshold at which you'll measure will calculate the ROC. Means how much gap in the data set that will give for each reading to calculate the ROC curve. So we have initialized the delta. So this is, we run this ROC curve. Or did I finish running the, okay, yeah. Then here we are trying to get delta, we are changing delta to 0.01 and we are getting the get ROC curve by passing this whole function. Now we'll plot the ROC curve. As I discussed in the slides, you remember the peak, if the value is closer to 0 and 1, sorry, to top left corner, it means we have a perfect classifier because specificity and sensitivity both are high. So basically, a peak towards the leftmost corner will mean it is a near perfect classifier. The ROC curve, this ROC curve tells us that our model is a perfect, nearly perfect classifier with high accuracy because you can see the high accuracy. Now, what if we had calculated this by random predictions? So here, instead of using the ROC proper classifier we use, we are making a random probability, random classifier. So we define a random where we initialize randomly the values of all the values. And you can see these are the values that we get. So, and then if we try to call the get ROC curve using those values, oh, sorry, I didn't run this. Okay. Now, if I plot the ROC curve for these random values, see, here we can see that these random prediction values are all close to the mean itself. So we can clearly see that it's not a good classifier because it's not giving us the right accuracy at all. Now, ROC AUC score. So ROC, we have already discussed what it is. AUC basically means area under the curve score. Basically, we have to find the area under the ROC curve. That will give us the ROC AUC score. Now, let's go for the classifier that we got, ROC classifier that we got right. So we can see the area is nearly that area of a square. We can say 1 into 1, so it will be nearly 1. But for this random, it is near the mean. So we can say it's close to the area of triangle, which is like half into 1 into 1. So basically close to 0.5. Let's validate that. So we'll check the AUC score. So we are defining a function where we are getting the ROC AUC score. Basically, we are taking the area under the ROC curve. That's what we are doing in this function. The cumulative difference between the difference in the x-axis, what we are doing. We are taking a difference and adding up all the values to get the area under the curve. So AUC score. So we can see the AUC ROC score is 0.98. Yeah, so area is close to 1. That is, it's not exactly 1, right? Because it's not going exactly along the y-axis and then turning a right angle to the x-axis. So it is close to 1. This is basically a good ROC score because getting 100% is not possible, and it's possible, but it's not likely. So getting this high accuracy is quite good. Now, if we had chosen the random predictions, in the random prediction, we can see that the AUC ROC score is 0.5080. So it's very close to 0.5. These minor diff like 0.0580 and all, it's due to Skillet's implementation. So there will be some granularity of thresholds. So this is what we mean by evaluation of matrix. The evaluation of matrix is very important if we want to get a proper model so that we can evaluate our own model and try to make changes in our model so that we can get a proper model that will give us the best accuracy possible for us. Any doubts? Any? Can Stratify be used for any data? Yeah, Stratify can be used anywhere. So basically, I'll show you the model there. Just a second. Mm, just a second. Where are you? Huh. So basically, when we are splitting the data for any model, irrespective of model, what it will do is for whatever the data set that you pass in. So basically, basically we are passing this trained data set that we got from the X and Y. So we'll be passing that, and irrespective of what it doesn't matter which model you're using it for, it will divide it into such equal proportions that will have equal representation of each data. Did I clear it out? Any other doubts? If not, I guess then I'm done with mine. So now Jay will be continuing with teaching about NLP and how it works. Jay, you may proceed.
Yeah. Okay. Okay. So I will be going through like basic concepts of NLP, like only basic concept only. What is NLP? Like NLP is a field of artificial intelligence and machine learning that gives a machine or a computer ability to read, understand, or derive meaning from human languages. So that's basically like NLP. So like where are the application of NLP? So like you must have noticed like whenever you search something on Google about some product and you start getting advertisement regarding to that product. Like that is also one application of NLP that is called like whatever keyword you search on a search engine. So like whatever the user gets an advertisement which has similar keywords like whatever you search on the search engine. That's one. And like email filtering. So you must have noticed like some emails automatically goes to spam and some automatically goes to like not spam. So that's a one that also a application of NLP. Speech recognition. So like okay Google and Siri. Sir. So all works on the concepts of NLP only. Sentiment analysis, like analyzing the sentiment of the audience, like whether it is positive or negative. That also can be done through NLP. So the so like that's about how GPT-3. So GPT-3 is a language model that was created by OpenAI. It's like GPT-3 is the most 5 billion billion learnable parameters. So like the weights, so it has 175 billion weights to learn. So let's see this video. Like it's a video. Like, it was just it was just created by GPT-3 alone. Like it was not supervised. It was unsupervised. It was just both the conversation was developed by GPT-3 only. The whole conversation is developed by GPT-3. So I will just play a little bit. Like you can watch the video if you want. Okay, so what I do is I'll just upload the video on the WhatsApp group and you can watch. So like the whole conversation was only developed by OpenAI, the GPT-3 model without any supervision. So like that's a super cool. So like there are huge amount with where GPT can be used. Yeah, GPT can be used in coding. It can be used in writing essays like without any super to convert any language to convert languages to other languages, etc. So like there is a little like this clip which shows like how can you do coding with GPT-3. So like you can improve the runtime complexity of the function. So you write a function and you provide an instruction that I want to improve the runtime complexity of the function, and GPT will do that for you, and it will write code with improved runtime complexity. You don't have to do anything. You just have to write the instruction. I want to increase the runtime complexity, and it will do it for yourself, for you automatically. Like if you want to convert code into another programming language, it can do that also. See, like it converted that Fibonacci sequence code in Python to JavaScript. It's- So like if you want to increase the runtime complexity, that it can do. So let's talk about basic concepts in NLP. So let's talk about corpus. So what is a corpus? A corpus is defined as a collection of text documents. For example, data set containing news is a corpus. For the containing Twitter data is a corpus. So you can you can imagine a corpus as a book. So a book has like different pages. So different pages. A corpus consists of documents. Document can be considered as different pages. Like a single page consists of different paragraph. That paragraph, and then a paragraph consists of different sentences, and a sentence consists of different words, which are called tokens in NLP. So what is tokenization? Units are called tokens. So it is a process of dividing our like whatever we have like paragraphs and documents into words which are called tokens. So we give each word a unique number to identify that word. We give each word a unique number. That is called tokenization. What is stemming? So stemming is used to normalize word into base form or the root form. So see. For example, like we have multiplication. So converting multiplication into multiple, that's the base form of that multiplication word. That is called stemming. So stemming and lemmatization are both almost same, but what's the difference is, for example, in stemming, you have multiplication. So in stemming, what it will do is it will just truncate that part. It will cations part. It will just keep multiply. So like it can generate word which doesn't have meaning, but lemmatization will always generate word which have meaning. So this is the example of lemmatization. So for example, like multiplication will get converted to multiplication, then multiplicate, and then multiple. So all these words will get converted to multiple. That's the root form of all these words. That's how lemmatization works. So natural language processing tasks mainly involve two types of analysis. One is semantic and one is syntactic. So in semantic, what we do is in semantic we try to guess the meaning of the sentences that we are given in semantic analysis. In syntactic analysis, what we do is we try to analyze whatever we like. It identifies relationship between different words. For example, word which is noun, which is pronoun, etc. So, so like we can't just put the words into neural networks to guess to do NLP task. We need to convert a word into vectors. That's like machine only understand numbers, so we need to convert words into text into vectors. So encoding is, for example, we have three words, so our vocabulary size is three. So what we do is we assign each word a number. So for example, uh, we assign Vishku as 1, Torgensen has 2 and Dream has 3. So what we do is we have vocab size of 3. So what we do is we generate a vector. Like for example, Visco is assigned number 1. So is assigned index 2. So there will be one at the index 2 of that 0 vector. Similarly for Dream is assigned 3. So there will be one at the third index of that 0 vector. So the length of the vector will be the size of your vocabulary. So for example, this like they are base type. So arc bridge type is assigned this vector. One like it will be assigned one at first index. Beam is assigned as second. So there will be unique position where the vector will be non-zero. So for different words, we will have different one hot encoded vector. So this is called one hot encoding. So let's talk about word embedding. So what's word embedding? So word embedding is representation of words which computer can understand and it encodes the meaning. So for example, if two words are similar in meanings, they should have less cosine distance. You know what is cosine distance? So if two vectors are pointing in almost same direction, they will have less cosine distance they will have less. But if they are pointing in sorry, yeah. So if they are in pointing in same direction, cosine distance will be more. But if they are pointing in like different direction, the cos of the angle between them, the cos of angle between them will be less. So what embedding is we what we do is we try to embed those one hot encoded vectors into like real valued vectors such that if two words have similar meanings, they should have larger cosine that larger cosine value. Word to back is simply like converting one hot encoded vectors. So for example, let's say we have vocab size of 10,000, but like we want to convert like 10,000 is huge. Like sometimes we can have 1 million in vocab size of million. So what word to back does is it reduces the dimensionality of the vectors. So for example, like we have vocab size of 1 million, so we can convert it into like any number which is like we can convert it into any number which is less than 1 million. So this is the like for example, like we have like vocabulary of 10,000 words, but what we are doing is we are converting it into like so the 10,000 we have vocabulary of 10,000 words. So one word encoded vector will have length of 10,000. But with embedding, what we are doing is we are reducing the dimensionality of our here to compute. So there we can like there are two models with through which we can obtain word to vec. One is continuous bag of words, one is skipgram. So continuous bag of word is, for example, like we are given a word, like in a text we are given a word and we try to predict the the words in the neighborhood of that word. We can define like until until like we can define the window size like until what word we have we want to predict. And skip gram model, what it does is we are given the context word, like the neighborhood words, and we try to predict the center word. So like this is a skip gram, so we are given a center word. What we do is we try to predict the words which are ahead of that and which are previous of that word. And in given the neighborhood words and we try to predict the center word. So there is a one more thing called as term frequency, inverse document frequency, which is also used to represent words in terms of vectors. So what is term frequency? So for example, let's say we have different documents and like different documents have different words. So what is term frequency? Term frequency is the number of occurrence of a specific term in a document. So what term frequency represent? It represents term frequency represent every text of the data as a matrix whose numbers are the number of documents, rows are number of documents, and columns are number of distinct terms. Please. So see this. So we have 6 documents, and like they are, for example, like there are 7 words. So what this is the term frequency matrix. So what it does is, so for document 1,000 and 1,002 times in document 2. So like this is that one. So for example, sports occurs 76 times in document 1, 80 times in document 2, 100 times in document 3, and so on. So that is the term frequency matrix. Then we have inverse document frequency. What inverse document frequency is that it try to reduce the weight of a term if terms occurrence are equal scattered throughout all the documents. So for example, if there is a word which is scattered, like which is present in like 6 documents, and there is a word which is present in only one document. So the weight of the word which is present in all 6 documents will be less than the weight of the weight of the word which is present in only one document. So for example, like this. For example, we have like 3 documents. One is one. Another one is I like image processing. Third document is I like signal processing and image processing. So this is the term frequency matrix. So what you're doing is and occurs 0 times in text 1, 0 times in text 2, and 1 times in text 3. Similarly, we will do for all distinct words. We will create a term frequency matrix. Now for inverse document frequency is given by n divided by DFI. So what is n? N is the total number of documents. And DFI is the, for example, if we have a ith word, so DFI is the number of documents containing that ith word. So for example, if number of documents containing that word is more, this value will be less. And but if the number of documents containing that word is less, this value will be more. So it's like it if it is scattered, this value will be less. If it is not scattered, this value will be more. So similarly, this is what we are doing here. So we have like different words. We are calculating inverse document frequency for all those words. And for like what TF-IDF does is it multiplies both these things. So for example, we have this matrix and this matrix. So we will multiply both these according to the formula written here. So after multiplying this, you will get this matrix. So like what what this what this technique does is, for example, if you search something on search engine, so for with the help of TF-IDF by TF-IDF value, search engine can give us most relevant documents. So we can search like which documents has the which document has are less important. So with the help of this thing, we can determine like which document is less important and which document is more important. So how do we train our model for NLP? So what we do is, for example, we have text. What we do is we convert into one hot encoded vectors. Our whole text we convert into one hot encoded vector. Then we do embedding, which reduces the dimensionality of our vector. Then like we have tags, so we just it's like a simple training only. Like we have text supervised training. We have text. We predict the value, then we calculate the loss, and then we try to minimize the loss. And so then in prediction, we have text. We convert again it into one hot encoded vector. Then we do it embedding, and then we just try to predict whatever we want to. So now these are the basics, like the how we represent words in machine in natural language processing, so that computer can understand whatever we are trying to convey. So now I will show you a model. Like I created a model which can analyze the sentiment of the news headlines. I'll show you that. Okay, so this is the thing. So we have a data set called as sarcasm.json. So we are importing that data set. So it has like different news headlines which tag whether it is sarcastic or not. So we are just reading that data set. So it has two columns. One is the headline and another one is the headline and another one whether the headline is sarcastic or not. So what we are doing is we are just we are appending the sentences into our sentence list and labels into our labels list. So we have a vocab size of 10,000 and embedding dimension of 60. 10,000 dimension of vocab size to 16. So we are like importing tokenizer. Tokenizer will do like it will assign a unique number to each unique word. So we are just applying that tokenizer on our text data set. And what is paired sequences? So paired sequences, for example, we have like there are different sentences which have different length. So what paired sequence does is if one sentence has less length than another sentence, so it will add zeros in the end of that sentence, so to make the length of both sentences same. So the neural network is really shallow. We just have an embedding layer, then we have a average pooling layer, then simply fully connected layers. We have two fully connected training our model with model.fit. So like we are just graphing the loss and value. So now we are testing. So first headline is scientists to kill duck to see why they are dying. So this is really sarcastic. So like they are killing ducks to know why they are dying. So it predicting that it is 0.999%, like it predicting that it is 99% sarcastic. So it is working really well. And like woman missing since she got lost. So this is also really sarcastic. So it is predicting it is 98% sarcastic. This is also like really well. It is working really well. So I am not going in details of this code. If you want, like you can ping me on WhatsApp group. I can like I can make you understand. I'm not going in the deep. So we are running short of time. Okay, so now Ashish will discuss about reinforcement learning, basics of reinforcement learning. So Ashish, can you please take?
Yeah, sure. I'll just pull up my presentation. Yeah, can someone confirm that the screen is visible?
Yeah.
Yeah. Okay. Cool. So here, guys, for the end of this series of some zero to hero in machine learning, we'll just be looking at an introduction, very basic introduction to what reinforcement learning is, and I'll leave you guys with finally with a model for one of the most fundamental reinforcement learning algorithms, that is the Q-learning. So let's get started with what we have for today. So first up, we'll just understand what is reinforcement learning and what are some of the fields where we use reinforcement learning. And after that, I'll explain to you some basic terminologies which you guys need to know if you ever decide to uh, dive into reinforcement learning more. And these terminologies will also be useful in understanding this session as well. And next up will be some very basic and fundamental properties of reinforcement learning problem and what those are, and that will be under the everything Markov title. And finally, we'll be seeing what the Q-learning algorithm is. So in reinforcement learning, very simply put, reinforcement learning is basically the science of making a decision. It's like how well can you make a decision. So what we do is we have an agent and we put it in an environment, and we want to train it in such a way that it takes the best decision in that environment possible. So one thing is, since reinforcement learning is in reinforcement learning, we basically don't have a supervisor. That is, we don't have any previous data sets to guide us to to tell us what is the final outcome that we desire. So here, if you put an agent in an environment, then the agent on its own has to learn what to do in an environment, and this is characterized by something which is called the reward. So we see what reward the agent receives, and we try to maximize that reward towards the end. So, and because we don't use any previous data, RL is actually a very robust algorithm and is one of the most upcoming fields of research in machine learning. So some of the applications of RL are in gaming industry. So gaming industry makes use of RL to train agents to play games, to play a lot of play games in Atari or Scratch, and learn how to play those games. And the results are like very fantastic. There have been in some games they've been able to outperform the best human players that are there currently. And next up, we use them in industry. Like reinforcement learning algorithms is used to train robots in industry to perform certain tasks. So, for example, there's the Google's DeepMind reinforcement learning algorithm that is used to cool their data center, and this also has helped them reduce around 35% of carbon emissions. So, if you guys are interested, you guys can see about Google's DeepMind as well. And one of the most important fields of reinforcement learning is autonomous driving. And various deep reinforcement learning papers, if you will see them, they are mostly pertaining to autonomous driving and functions such as path optimization, motion planning, and dynamic pathing for self-driving cars. And one more field where you can see reinforcement learning algorithms is finance. Now, basically, in finance, what happens is, if you have like a supervised ML model, now what it can do is it can help you to predict like future sales and stock prices, but it cannot tell you whether you have to hold on to a stock or let go of a stock. But RL agents, on the other hand, can tell you such information, so which makes them much better than supervised learning models. So these are some of the applications of reinforcement learning. Now, some of the basic terminologies that we'll be needing to understand reinforcement learnings are, so history. History is basically the sequence of action that your agent takes, and the observations that it can see, and the reward it gets from the environment. So now, as you can see over here, action history over here, you can see it's like a stream of data. So basically, O1 is the observation at timestamp 1, R1 is the reward at timestamp 1, and action is the action it takes at timestamp 1, and it is followed by O2, R2, and E2, and finally up to AT minus 1, OT, and RT. Now, here there's no AT because T over here corresponds to the timestamp T or a terminal state from where you cannot take any further action. So this is what. So history is basically a sequence of these observation, rewards, and actions for the environment. Now, what do we've used the word action over here very frequently, and you can see this A. So, what do we mean by an action? So, anything and everything that an agent does in an environment is what we call it as action in reinforcement learning terms. So, for example, say if you have an agent in a maze, then moving up, down, right, or left is called an action. As or suppose you have like a space shooter game in Atari, then moving left or right or shooting or blocking might be an action. So this is how we tell what an action is. Now here we also came across the term reward. So what do we mean by rewards? So rewards are basically they are a type of response that you get from the environment for every action that you take, and this is how what tells you whether the action you have taken is good or bad, and whether in future should you take this action. So usually it is a scalar feedback signal from the environment, and it tells the agent of whether the action is good or bad. And the final goal of any reinforcement learning problem is to maximize the total rewards that you can get from this environment. So, and one of the most important terminologies in RL is state. So, what is state? Because state is something that is used so much in RL papers and RL algorithms. So, a state is basically the complete summary of whatever has happened in your environment so far, and that will be used to tell so that to know what can happen next. So, in short terms, a state is basically a function of the history of your environment. So, uh, it is like whatever observations, rewards, and actions that you have seen or taken. So, a state is basically like a summary of everything that it is. Now, to give you a simple example, say in a maze environment, you were just entering the maze and you land on the first step that is there. So since you've landed on the first step and you can see like a particular maze environment from there, so that is like one of your states for that maze environment. And so also we have like three types of states that we commonly come across in RL. One of the so those three states are environment state, and it is usually denoted by ST with a superscript T. Agent state, which is denoted by an ST with a superscript A, and information state. Now, so as the name suggests, environment state is basically the environment's private representation uh, of the state that is there. So it is something that the environment sees and not the agent. So this usually is not visible to the agent. So the agent doesn't know what the environment sees in that particular state and how it conceives that stage is. But even if it visible, so it's not that all the information that the environment has is useful for the state, and as such is not sometimes visible to the state also. So there are some useful information that we use from an environment state to implement an algorithm. Now next up is the agent state. So it is the agent's internal representation of the state. So it is something that the agent sees, and this over here is very useful in implementing an algorithm, because at the end of the day, you want to train your agent, so it is very important to know what your agent is seeing. And information state is basically a combination of the useful parts of the environment state and the agent state. So it has all the useful information from the history. And so the final terminologies that you need to know before we can do anything in reinforcement learning is policy. So now what is a policy is basically the agent's behavior. A policy tells the agent what to do. So in simple terms, it is like a mapping from the state to an action. So if you are in a particular state, a policy will tell you what action you have to take next. Like for example, if you are in a maze environment and you are surrounded by walls on the upper and left side, so your policy would tell you to either go right or go down. So that is what a policy is. Now there are two types of policy. One is a deterministic policy. So a deterministic policy means that you have discrete actions to take. Like you have finite amount of actions that you can take. Like in a maze environment, you can only go up, down, right, or left. But say you were training your agent to play FIFA. Now there is no discrete action in playing FIFA, because there are no set number of actions in FIFA. So you can have a lot of different actions that goes from passing to shooting to moving around or doing a skill. So that is like a vast amount of actions which you cannot classify it as a deterministic action. Now, next up is a stochastic policy. A stochastic policy is basically it. Say your agent has a infinite amount of actions from which it can take anything, from which it can pick a particular action. So, stochastic policy is basically a policy which has a probability for each action that your agent can take when it is in a particular state. So a policy is denoted by pi. So uh, a deterministic policy is usually denoted by as pi of s, meaning it is a function of the state, and a stochastic policy is denoted as pi of a the probability of the action that you take in that particular state. So it is a probability function of the action for a particular state. Now, next up is the value function. So value function again is a very important thing that you need to know in an reinforcement learning algorithm, because sometimes uh, it is this value function that you're trying to maximize. So value function is basically a prediction of the future rewards that you are going to get. So it is, so when you're in a particular state, so a value function is usually associated with a particular state. And when you're in a state, the value function tells you whether this state is good or bad, and it will help you in selecting the next action. So a value function is usually denoted as V of S. Now a subscript pi means that it is a value function that is following a policy. So a value function is usually an expectation function that is of that has the rewards that you gain from the next action that you take and from the further future actions that you have taken, multiplied with gamma to the power n, where n is the number of times you are looking ahead in the future. Gamma times n minus 1, where n is the number of times you're looking ahead in the future. Now, what is this gamma? We'll come up with. We'll come to it later when we are discussing Markov reward processes. But for now, just keep in mind, this is how you represent a value function. And finally, what is a model? So a model is basically something that predicts the environment, that what the environment will do next. So say if you have a particular policy and you are in a particular state, so that policy will tell you what action you have to take, and it will send an agent in a different state. Now this different state is determined by a model. So a model will tell you what that next state is going to look like based on what action you have taken from the previous state. Now there are two general types of models. One is a transitions. So transition they basically predict the next state given your previous ones. So a transition is usually denoted by this P with a subscript of A and the superscript of A and a subscript of S dash, where S is the current state and S dash is the next state. So it is basically a probability of what the next state will look like given the current state and the action that you take, that is S and A. And next up is the rewards. And so rewards is usually denoted as R with a superscript of A and a subscript of S. And reward basically predicts what your immediate reward is going to look like. So it is basically an expectation function of the future reward given the state that you were in and the action that you took. So these are the basic terminologies that are very useful in understanding any RL algorithm, or any, if you want to read up any RL paper. So these terminologies will come up time and again over there. And so these are very useful. Next up, we'll be discussing one of the most fundamental concepts that is crucial to how to make an RL model, even if it is a very simple one or even if it's something very complicated. So now, so first up, before we go further, we need to know what a Markov property is, because a Markov property simplifies our task of solving any reinforcement learning problem. So a Markov property is something. So we say anything is associated with a Markov property when that particular thing is only a function of this of its when the future of that say if you have like a product, when the future of that product is say independent of its history, then we say that that product has a Markov property. So in RL, usually the states tend to have a Markov property, that is the next state which you're going to go in is only dependent on your present, that is the current state, and is nowhere dependent on what the previous states were. So so if you were to take a probability of the next state that you are going to land in based on the current state, that would be same as the probability of the next state if you were to consider all the states that you have been in. So basically you can see it by this final equation that is there. So the probability of the future state is only a function of the current state. And it is the same as if you were to take a probability of the future state with respect to all the states that you have seen. So this is the basic Markov property, and so surprisingly in reinforcement learning, for any environment, all states are basically Markov properties. If they are not Markov properties, it becomes very difficult to solve for them. So, and next up is a Markov decision process. So, a Markov decision process is formally describes an environment for a reinforcement learning agent. When the environment is fully observable, that is, you can see, you can, if you're in a particular state, you can see what is happening, what the environment looks like. So suppose you were, say, training a robot to work in a factory. So say if the robot was near the gate of the factory, and if your environment is fully observable, that means the robot will know what is happening around the factory. Even though it is standing at the gate of the factory, it knows what is happening, say, at the exit and say at any other place. So an MDP is used to describe the environment for an reinforcement learning agent, when you can like basically see what is happening in the environment. So an MDP is basically a tuple of the state and the probability transition matrix. So we came across the transition model. So a state transition probability matrix is this transition model that we use over here. So so before we go further, we try to understand what a probability state transition model is. So this matrix over here basically tells you what is the probability of going in the next of in a particular state from this current state. So it is like, it is a matrix which stores these values p of 1 1, meaning what is the probability of going to a state 1, that is the first term, from a state 1. So this obviously would be 1, but like it would have the dimensions n cross n, when n is the number of states. So here probability of 1 comma n is basically probability of going in the state n when you are in the state 1. So this matrix, so you can basically visualize like how this matrix will look like. So so a Markov decision process is basically a tuple of this matrix and the state, like the set of states that exist for that environment. And in any reinforcement learning problem, we are basically trying to solve for these MDPs. We are trying to find out the best possible probability model, and the from that particular environment. Now, one step ahead of MDPs are basically Markov reward processes. So a Markov reward process is basically an extension of the MDP tuple that we saw, that is the set of states and the probability matrix. And along with that, we have the reward function and the gamma that we call as the discount factor. So here a reward function for any state S at the time t is basically the expectations of the reward that you will get from the timestamp t plus 1. That is basically what are the immediate rewards that you're going to get from the future. So, and since you have been hearing this a lot, what is an expectation, and it like something is an expectation function. So an expectation function is basically something like it is like taking an average of a series of events, but here you also consider the probability of those series of events being repeated. So an expectation function is basically a mathematical term where the average of an outcome of a series is taken into consideration with the odds of them being repeated. So reward. So here we have the reward function, and finally the gamma, or the discount factor, which we saw earlier. So what is a discount factor? So a discount factor basically tells us, or it tells us the like right now, if we are in a particular state, how much do we value a future reward, like a reward that is not immediate, but you're going to encounter it sometime later in the future. So how much do you value that reward versus the reward that you'll immediately get from your action? So that is what your discount factor tells you. And so its value is usually between 0 to 1. So if your value is 0, that means you do not care about the future value, future reward that you're going to encounter in the environment, but you only care about the immediate rewards that you're getting, and you want to somehow maximize those immediate rewards. So we call this being as extremely short-sighted. And if your discount factor is 1, that means you only care about the future rewards. Like if you're in a maze, you had a discount factor of 1, meaning you would only care about getting out of the maze, but you would not care about taking actions that will help you reach the end. So this is something we call as being extremely far-sighted in a RL problem. Now, before we move on to Q-learning, we need to know like what are the reasons that we discount the reward function for. So one of the simplest reason is because it is mathematically convenient to use to discount the rewards. And another reason is we do this to avoid infinite returns in a Markov cycle. So what happens is, like, say suppose if you were to fix the discount factor to 0, that means you do not care about going to the get for future reward in your environment. So what you would end up doing is, like, if you're in a particular state and that action gives you a particular action gives you the maximum immediate reward, but if you follow that action at some point in future, you're going to end up, say, if it was a vehicle, self-driving vehicle, that vehicle would most likely end up falling in a hole. So but what would happen is, since you're fixated on the immediate rewards, you would keep taking that action because it is going to keep giving you the maximum immediate reward. But in the future, ultimately you're going to end up falling in a hole, so which will not help you train the model very efficiently. So this is one of the reasons why we use discount factor to basically maintain a balance between the future rewards and the current rewards. And the other reason is because the future environment is very uncertain. Like, we do not know what the future environment will look like once we go in the future in the next state. So discounting helps us to account for that uncertainty. So one of the main reasons why we use discounting is to make sure that that uncertainty does not affect our training of the reinforcement learning agent. So these are the basic terminologies that and basic fundamental properties that you need to know for reinforcement learning. And next up, we'll look at a very fundamental and a crude model of doing very simple reinforcement learning tasks. So here we'll be looking at something called the table lookup Q learning, which is used for implementing very primary and rudimentary environments. So what is Q learning? Now, Q learning is an off-policy learning algorithm. So what do we mean by an off-policy learning algorithm is, we will basically be using two policies to evaluate to train the agent. So one policy will be our behavior policy, based on which we'll take the action, and another policy will be the target policy, which will be the final policy which the agent will be using to do the task in that environment. So using the behavior policy, we try to train the target policy. So this is what we call an uh, off learning algorithm. So we usually we denote this behavior policy with mu, and so we sample from the behavior policy, that we take the states, the actions from the behavior policy and get the rewards for that, and we repeat that till we encounter the terminal state. Now, one of the main advantages of off learning algorithms is that this will help us in learning from other agents and humans. So, like, we can train our, like, say, a robot to walk around a factory based on a agent, based on, like, say, a human that knows how to walk around a factory. So we can, like, use that experience and use that to train our robot instead of, like, wasting that experience. So Q learning is like one of the best examples of off policy learning. So as I told you, here we use a behavior policy to compute the actual policy, and here we evaluate the value function or the action value function. So, and so you need not worry what an action value function is. An action value function is basically a value function with an accounting for what action you take in that particular state. So an action value function will give you the rewards for a particular state and what action you took in that particular state. So it is basically kind of like a 2D table which you can imagine. So in Q learning, we try to solve for this action value function So we'll look at what the learning algorithm of a simple Q-learning looks like. So we usually denote the action value function over here as Q, which is a function of the state and the action that we took. So if we are in a particular state and we take a particular action, so we update the action value function for that particular state action with this term over here. Now this term over here, uh, I'll explain to you what this term is. So alpha is what we call the learning factor. Is basically how quick do we want the agent to learn, and like learning factor helps finally determine over how many number of steps or episodes the agent finally gets trained. So here R is the reward that you get from your behavioral policy that you follow, and gamma, which again is the discount factor over here, and times max of q of s dash a dash is basically the q value of the state s dash, that is the future state in which you're going to land in based on the future action that you take. And max of that means you want to go to the maximum possible value of the action function corresponding to all the future states that you can go to. So this term over here comes from the target policy that we want to train. So gamma over here is basically going to discount it, is going to tell how much do we value the future versus what the present is, and we subtract all of this from the current value of the action value. And so we then we use the entirety of this to update the current value of the action value function, and this finally converges to what we call the optimum action value function. So this will be if you guys have not understood this right now, don't worry. I have trained a very simple Q-learning agent, and there I'll explain to you how. There I'll be explaining to you all of this in much more detail, and you will get. I hope that you will be able to understand that. If you have any doubts, you can ask me uh, over here. So we'll be seeing how to basically do a Q-learning on a Python gym. Now, gym is basically an inbuilt library in Python which has many environments on which you can do reinforcement learning and play around with them. And they are basically predefined classes with state spaces, with the states that exist and actions that are there, and what are the rewards that each action will get you. So here we are going to be training something that is called the Taxi V3 environment, and we'll apply the basic Q-learning to it. Now I will be explaining to you what the Taxi V3 environment looks like, but if you guys have any doubts regarding it, you can use this documentation to see what the Taxi V3 environment is. And right now I haven't shared this Colab notebook because this is purely for demonstration purposes. After the session is over, I'll be sharing this notebook with you, and you can see the code for yourselves. So a taxi environment is basically this small table that you see over here, where you have four corners R, G, B, and Y. And so over here, what you do is you basically you and this yellow block over here is your taxi. So what you have to do is you have to train this taxi to basically pick up the passenger from where this blue spot is and drop it off to wherever this purple spot is. So in in a random environment that you try to create for taxi, you can have this blue spot on either of these four letters, and the violet spot on either of these four letters. So here you have few walls like these, and on the edges as well. So your taxi is spawned at a random location. So you should train the taxi to go to this passenger, pick it up, and then finally learn to drop it off. So here I have imported the gym, and I have created the environment for the gym on this variable game environment. Then I have generated the action size, like what are the possible actions that are available. So this taxi V3 environment has a deterministic action spaces. That means it has a fixed number of actions, and there are 6 actions that your agent can basically take. So of the obvious, the four of them will be moving up or to your right or to the down or bottom or left. And the fifth action is picking up the passenger, and sixth action is dropping of the passenger. So, and I have also sampled the. I have also given you what are the total states, that total number of states that you can have in your taxi environment. So there are a possible of 500 states that you can have, and the 500 states comes from the fact that you have basically 25 states. You have basically 25 positions over here in which your taxi can be in, and then you basically have like four basic tasks with which your taxi can move, and then you have four and another four comes from the fact that there are four types of things that you could do, that is pick off correctly and drop off correctly, or you can like pick off correctly and drop off wrong, or you can like uh, you can not pick up and not drop off also. So from those four, so you can do the multiplication, and that I think that should render I think 500, if I'm not wrong. So here I have basically trained an agent to learn in this, to learn for a period of 25,000 episodes with a learning rate that is alpha of 0. 0.6 and a discount rate of 0. 0.9, meaning I am like very heavily focusing on future rewards but not completely ignoring the immediate rewards. And so here I'll be explaining to you one of the important factors that Q learning algorithm has, that is the exploration exploitation trade-off. So if so as you had seen in this learning algorithm, you have something that is called a maximum of a of an action value function. So when you're in an environment and you try to take something that is a maximum of everything possible that you can take, you call that as exploitation, meaning you know what are the future states that you can go to, but you want to go to something that is a maximum and which will like help you gain more rewards. So that is what we call an exploiting the environment. But instead of that, say you were to just follow the behavior policy and go to the future state based on an action and get this reward R. So what we say, that we call that as exploration, meaning our agent still does not know what is the best possible action. So we want the agent to look around the environment and try to, like as the word suggests, explore more what the environment has to offer. So one of the key aspects of reinforcement learning is trying to find a balance between the exploration and exploitation trade-off. Because like in the starting of the agent's training, you want your agent to basically try and explore as much as possible and try to learn about the environment as much as it can. But as you keep on training it, you don't want to be stuck in exploring, because now you have data about the environment. So what you want it to do is, you want it to exploit the data that it has gathered from all the exploration and do actions that will give it the maximum future reward. So you want this to happen towards the end of your training. You don't want it to happen immediately after you start training it. So a key thing is to find the balance between this. So here what we do is, here we use something called an epsilon greedy method to train to balance this exploration exploitation trade-off is. So we take a value of epsilon. So here we have taken a value of epsilon of 0.4. So what 0.4 means is, with a probability uh, of 0.4 or values or less than that, the agent will explore. So here if you see, if you get a value that is less than 0.4, your agent will explore. But with a probability of 1 minus epsilon, that is 0.6, for every value that you get that is higher than 0.4, your agent will exploit the environment. So, and what we do is, we take a decay rate and we decay this epsilon, because as the agent keeps training, we finally just wanted to exploit the environment. So this here is how we balance the uh, exploration and exploitation trade-off. And here finally, this is the equation that I showed you guys in the slide, this equation over here. So this is the equation, and if any one of you are curious, this is what we call the Bellman optimality equation. If you guys are curious, you can look that up. But so this is that equation, and we'll finally train this agent, and I'll show you guys a graph of the average rewards, maximum rewards, and minimum rewards for every 2,500 episodes of the 25,000 training episodes that we run. So I'll run this code and I'll show it to you guys. So as you can see, this agent over here. So what it did was it got it spawned here. So it immediately went to pick up the passenger from the blue spot, and then it did a drop off at the B spot very very efficiently. So here you guys can see the graph that has been generated. So you guys can see like approximately after 5,000 episodes, the agent learned how to do the best possible actions to pick up and drop off the passenger, and you can see there's a saturation of the maximum reward that the agent can extract from the environment based on the based on the reward values that have been defined for this environment. So this is all from my side for introduction to reinforcement learning. If you guys have any doubts in any of the topics that were taught today, the four of us are still here. You guys can either unmute and ask, or you guys can like put it in the chat box. And sorry for overshooting the time a little bit.
So anyone has any doubts? If not, we'll be ending the session now.
I think we can wrap it up, Anshu. I don't know.